Thank you so much, sir, for those words. It's an honor for me to be here present at this event, such an important event in ergonomics. So thank you. My name is Cristina Herrera. I'm one of the scientific leads of the Canadian Institute for Safety, Wellness, and Performance. And as Trevor mentioned, today I'm going to present protective or problematic shoulder passive exoskeleton use and musculoskeletal risk in overhead work, a field to lab approach. So, sorry, again, it's probably, can you, trying to, there you go, awesome, thank you. All right, so our research institute, the mission across all the workers' lifespan is to enhance safety outcomes for workers across Canada, to support the mental health, the quality of life, enable a healthier, happier careers and retirements. Also to boost workplace productivity through evidence-based practice, and to invest in every stage of the working life, from the early career, throughout their careers, through injury prevention and potential recovery and potential insertion again into the workplace, and ultimately for retirement without any MSDs. So Canadians construction industry. So construction workers are 1 out of 13 working Canadians and is the integral part of our Canadian economy. The construction workforce is at 15% higher risk than the general working population for sustaining an injury. The MSD disorders make up to 40% of all the workplace injuries and lost time claims. The shoulder injuries represent the 12% of all those MSDs, and it is very high in some trades such as brick stone, masonry, and drywall finishing. The overhead work is considered to an increased risk of the appearance of these shoulder injuries. So let's talk a little bit about overhead work. So what does the literature says about risk threshold for overhead work? So as you can see in this chart, we have two main metrics that are considered risky: the duration of overhead work and the frequency of those overhead actions. First off, we have to define what is an overhead action, what is an overhead work. Most of the literature says that an overhead action is whatever crosses the threshold of 60 to 90 degrees of shoulder flexion. So if you look at the duration of overhead work, whatever crosses the threshold of above 10% of the total task time or the total shift duration, that will be considered a high risk. Similar to the frequency, whatever crosses the threshold of 1 posture change per minute, that would be considered a high risk. So I'm going to show some of the field studies. I'm going to highlight some of these overhead work risk that we saw in our studies. So we capture continuous posture through the placement of an accelerometer in the lateral part of the arm of 3 glaciers that are like glass straight persons, and they were tracked over 9 days. As you can see, the duration above the shoulder was 4.3%, which corresponds to a moderate risk when it comes to the threshold. The muscle activation, we saw an average value of 3% of muscle exertion, which is below the 15% of MBC, so it would be considered a moderate risk. However, the frequency of those overhead actions, it's around 1.4, which is above 1 minute per threshold. So that is under the category of high risk. So we see moderate and high risk in these studies. Same with another study that we conducted. We also placed that accelerometer in the lateral part of the arm, and that was tracked continuously, the posture. And we also track the muscle activation and the rates of perceived exertion at baseline, mean point, and end point of 2 consecutive days in 35 workers. So we saw that the higher arm elevation, duration, and frequency increase the activation of the anterior deltoid. This anterior deltoid, for those who don't know, is the main muscle for shoulder flexion. And it increased the activity by 20%, which leads to fatigue. Also, the workers report increased exertion in the shoulders, in the upper back, in the arms, during these repetitive overhead tasks. And this leads to cumulative fatigues over shift that increase the risk of injury due to insufficient recovery time. So what led us to think all those overhead postures over time, these moderate and high risk, lead us to think about potential solutions to overcome this. So one of the potential solutions is the passive shoulder exoskeletons. We know for sure that the passive shoulder exoskeletons has been proved to reduce muscular support, to counter the forces during this overhead work, and also to provide shoulder relief. However, there are still some gaps in the literature that needs to be addressed to promote the implementation of these devices in the workplace. The number one gap is that there is limited research on the worker's perception and acceptance of this device. So let's jump onto this gap. So the previous study that I was mentioning before related to overhead work, we also assess the perception and the acceptance of exoskeletons. So the workers, we have two groups of people. So we have 40 field construction workers that they were using the exoskeletons for 2 days, and they were just using usual method for 2 days. So we asked the participants to perform their daily activities as they were do in a normal shift of work. And we track the posture through the accelerometer placed on the lateral side of the arm. And we also track the muscle activation and the rates of perceived exertion. And we asked them how they were feeling about the exoskeletons at pre, mid, and post shifts. So our participants, of the 40 participants, 80% of them were under the age of 35, and 93% were male. The majority of these participants were carpenters, electricians, and drywallers. And 1/3 of these participants worked on a residential work sites, and the other third worked in modular construction. So this is a graph showing what we track. So as you can see in the screen, we place the accelerometer on the lateral portion of the arm, and through a trigonometry model, we converted the accelerometer outputs into angles. So if we cross a line across 90, if we place a line there, that would be our threshold for overhead actions. Whatever crosses that threshold, it would be considered an overhead action. So we also created different metrics to understand this data. So based on those, which is the integral of shoulder flexion and time, we can see that during the exoskeleton conditions, the participants perform more overhead work. This could be related to multiple reasons, but one of them could be that the participants self-selected more overhead work because they were supported by the exoskeleton. So we also saw some changes in discomfort in the upper back and in the mid back from the beginning to the middle of the shift. And we also track what was the tasks that were more helpful for the exoskeleton. So workers report that lifting and positioning materials were helpful while using the exoskeleton, for example, top track for studs, electrical conduits, ball head, and ceiling drywall, for example. We also said that whatever task that they have to extend, they have to keep their arms extended, were also helpful. So nailing in top track with shooter, drilling metal studs into the top track, and other tasks, as you can see in the screen. Other tasks include pulling wire, tying in electrical boxes for lights, smoke detectors, mudding, tapping, especially for ceiling joints. So there were other tasks that the workers didn't find comfortable with the exoskeleton. So some of these tasks are reported, like, for example, tasks in tight spaces that they have reduced mobility, such as framing work around ducts, vents, working in closets. And also, for sure, tasks that are below the shoulder height. So the exoskeleton gets triggered when it passes that threshold of 90 degrees of shoulder elevation. So whatever is the, when the participants were going down or like had to perform something that was below that shoulder height, such as drilling the drywall below shoulder height, installing channels for metal stud framing, they did not find the exoskeleton helpful. We also asked the participant whether they agreed or disagreed with 5 statements about the exoskeletons. And most of the participants found the exoskeleton was easy to use. Over half of these participants found that the exoskeleton was comfortable, while less than 1/4 found that it was uncomfortable. For 70% of these participants, the exoskeleton did not hinder their work performance or the productivity, and improve the performance and the productivity. So we also asked what variables contributed to the exoskeleton use. And we know we have, for example, effort that the exoskeleton contributed the most. However, we have some tasks related to maneuverability that will still need to improve the design of these exoskeletons to improve maneuverability, thermal comfort, and feel. So 65% of the workers said that they were likely or very likely to use the exoskeletons if they were available through their employer. Some design recommendations. First off, it has to be compatible with other tools or PPEs. It has to provide sufficient mobility to assess tool belt. It must have the ability to adjust the level of support and resistance. It has to be feasible to be used in in tight spaces, and it must have a close-fitting design to allow the worker to move around with freedom, and it must have breathable materials to avoid heat and to provide thermal comfort, and also some mechanisms to prevent debris from entering the arm cons. And most importantly, these exoskeletons are not designed for everyone. So female participants were reporting sizing and fit issues. So for the gaps number 2 and 3, there are no guidelines of what is the maximum load that we can handle while using these exoskeletons. And also there is an unclear influence of the risk perception and workers' behavior. So I'm going to jump now to these 2 gaps. So the gaps that we saw in the field, or the needs that we saw in the field, we decided to tackle them through a lab study. So the objectives of this lab study were to determine these loads, these maximal permissible loads for unilateral overhead work, to examine how these loads vary by the body shape and by using a shoulder passive exoskeleton in males and females, and to assess whether these exoskeletons influence the risk perception, and by comparing the self-selected weights versus the actual muscular effort. So the first day of this lab study, it was a familiarization and 3D assessment of the anthropometric measurements. So after they were screened for eligibility and they provided consent form, we asked them some questionnaires, demographic questions about age, sex, and other questions related to their occupation. And then we performed an anthropometric body scan, where it consisted of a markerless system where the participant is placed in the middle of the lab. And through just a 5-second scan and a 5-minute processing, we have 36 anthropometric variables of the entire body. They also had an orientation with the exoskeletons, where they were able to practice and to ask questions about the upcoming sessions. So for the upcoming sessions, which are interventions, day 1 and 2, which is one day performing the task with the exoskeleton and the other day performing the experimental setup without it. So the participants had to perform simulated drilling task against a load cell, and they had to maintain a 70 newtons force, which these replicates a realistic scenario of drilling, and following auditory cues. So every 12 seconds, they will hear this cue, this beep, and they will have to drill until they reach 70 newtons and come back to the initial position. And they repeated this, so they have 3 conditions. One, it was performed at 90 degrees of shoulder elevation, the other at 120 degrees, and the third one at 150. And each condition lasted 5 minutes. This was a psychophysical study, which means that they had to choose the weight that it was comfortable for them. So the prompt was, choose a weight that is comfortable for you. Think about performing this task for 8 hours, even though the experiment only lasted 20 minutes, and choose a weight that you know that you can handle, but also you are doing your best. So they were able to modify the weight at any point. And we track electromyography at the muscles, at the anterior, at the middle, at the posterior deltoid, which is our all shoulder muscles, and also the lats and the biceps. So for the anthropometric, so related to data processing and analysis, as I mentioned before, 36 measurements were collected, extracted from the anthropometric, from the scan, but we only selected 5 measurements for analysis that were related to the exoskeleton use, which were height, waist circumference, upper arm length, upper arm circumference, and bust circumference. Through an algorithm that is called k-means clustering, we identify 3 body archetypes for males and 3 body archetypes for females. So we have a small, medium, and large for females, and a small, medium, and large for males. So when it comes to the processing and analysis to create this maximal permitted overhead loads, we stratify the loads by sex. So we created tables for females and males, and we also divided by intervention. So we have our controls and our exoskeletons. And we also divided by the condition. So it was either 90, 120, or 150 degrees of shoulder elevation. We created thresholds computed in percentiles at 10, 25, 50, 75, and 90, which these replicates previous psychophysical tables, very well known by Snook and Suriello. And we assign participants to the load that they were selected through the experiments. As you can see in the screen, those are the 3 conditions that we track. When it comes to muscle activation, we collected our raw EMG, and we filter it to subtract the bias, and we filter it and to remove the cardiac noise. And we got our final EMG amplitude that it was used for the analysis. For the statistical analysis, when it comes to maximal permissive overhead loads, so we use a multivariable mixed linear regression. And we account for random intercepts, accounting for the participant level. And our predictor variables were the sex, the intervention group were either exo or control, the shoulder angles, and the body archetypes, and age. For the muscle activation, we performed a linear mixed model, and we created one model per muscle. So we have 5 muscles. And our predictors were the exoskeleton use, age, sex, the shoulder angle, the drill weight, the archetypes, and the repetitions. So our participants were 62% males and 38% females. And this was a big, so we were able to capture a lot of females considering the small amount that is in the skill trades. So most of our participants were carpenters, electricians. And regarding the results, so we know that the exoskeleton increased the drill weight capacity by around 400 grams. So when they were using the exoskeleton, they were able to handle 400 grams more than the control. So for the smaller people, the smaller built people, they selected around 300 less weight than the larger archetypes. So we didn't find any differences between the medium and the small built individuals. We saw that the males participant handle around 300 more weights than the females, and there were no differences in the shoulder elevation on the drill weight that they selected. So what does it mean? So first off, it means that we need more ergonomic interventions beyond the exoskeleton support. So we know that the exoskeleton might improve this overhead lifting capacity and also the perceived safety, especially at higher arms elevation and among certain individuals, particularly males with certain anthropometric characteristics. These results provide guidance on how can we implement these devices for overhead work and to support improved drill design and to offer recommendations on the use on construction settings. For the muscle activation, we saw that the exoskeleton use decreased the anterior deltoid activation, and this kind of like leads to, okay, this is supporting the shoulder elevation. So the muscle activation was decreased for the anterior deltoid. However, for other muscles, such as the posterior deltoid, it was the opposite. So we saw an increase in activation. So when the posterior deltoid is the muscle that activates when the shoulder goes down. And if we think about the movement that they are performing with the exoskeleton, they have to go and they have to like break the resistance of the exoskeletons to go down. So that's kind of like also leads to fatigue. So what is the trade-off, right? We have some muscles that we are decreasing the activation, whereas others are increasing. Also, the drill weight influenced this. So the more weight that they put in the drill, the more activation that they got in the muscles. And we also saw some differences in the archetypes. So the small build individuals show an activation increase. So they had to increase the muscle activation to be able to perform the task correctly. So this leads us to think, as I mentioned before, that the exoskeleton reduce the muscle activation of some muscles, but also increase the muscle activation of other muscles. So it's kind of like redistribution the muscular demands. We also saw that the body types affect these muscle activation patterns, and this supports the idea that we need to personalize ergonomic intervention for the exoskeletons. All this lead us to more adaptive muscle balance exoskeletons to reduce fatigue and to better fit female workers and diverse body types. So this led us to a big project that it's called Multivariate Occupation Specific Anthropometric Database, or how we like to call it, Mosaic. So CISWP considers the capabilities of the worker to make more inclusive, safer, and health equitable through a better design of PPE, tools, and equipment. So the objective is to create these designs of PPEs and products to understand the needs and to improve the design's requirements. So the idea is to create a database that is not only sector-specific, but also job-specific, and to support the manufacturers for tools, equipment, and PPE to make products for Canadians' population. The goal is to, in the upcoming 3 years, is to collect 10,000 workers in the constructions and in the paramedic sectors. The current anthropometric database that we have, it is based on general population rather than industry-specific populations. This is not a Canadian population and is very outdated. So they don't consider measurements such as body measurements, parameters, age, sex, race, ethnicity, among others. So in the scientific literature, a poor fit, it is related to injuries. And also a poor fit, it is related to the low utilization or the low acceptance of this PPE in the construction and in the paramedic sectors. Studies have shown that consistent use of PPE reduces the likelihood of these accidents and injuries up to 1.5 times. And just in the construction sectors, the proper use of PPE could prevent 37.6% of the occupational injuries and disease. So CISWP will use this cutting-edge research technology that includes body scanner systems, portable scanners, foot scanners, in-body muscle to fat ratio scanners, strength testing, to develop this comprehensive and occupation-specific anthropometric database. The Ontario Mosaic database will help the Canadian workers to benefit from properly fit and effectively designed PPE, tools, and equipment, and also remove barriers that are faced by underrepresented groups. So the impact is that with this new anthropometric database, it will help Ontario businesses to meet the requirements of the Regulation 6123 by ensuring properly fit PPE for all body types. And of course, they will support to reduce injury rates and to make healthier and aging workers. So I will show now a video of Mosaic. Let me share my screen with you.
Equipment and PPE may not have accounted for this variability in their designs.
Product designers have relied on outdated datasets to design workplace tools and equipment.
Ill-fitting workspaces affect the way we perform our jobs, increasing injury risk and creating barriers for equity-deserving groups of all shapes and sizes.
In order to design for Canada's diverse population, our team at the Canadian Institute for Safety, Wellness and Performance is developing a new data set that will transform product design and will help make Canadian workplaces safer, more productive, and more inclusive.
We want Canadians to enter and prosper in valuable sectors, including skilled trades, healthcare, and first response. With new workplace regulations to ensure that equipment accommodates Canada's diverse workforce, we need the necessary data that represents the body dimensions of the Canadian workforce. It's a big challenge, and we are taking it on. We're developing detailed databases of anthropometric body dimensions and functional capacity through our partnership with Ontario's Workplace Safety and Insurance Board. This means collecting sector-specific and job-specific data from the Canadian workforce and collaborating with Canadian manufacturers of tools, equipment, and PPE. It's all part of our Mosaic initiative, supporting Canadian workers and Canadian businesses.
Our Mosaic initiative uses state-of-the-art technologies to capture the unique measurements of different body types, but also their strength and mobility. We will be doing this in our Stride Laboratory in Cambridge, Ontario. CISWP has Canada's only lab-based and portable 4D measurement system that can capture static and dynamic body dimension data in the Canadian workforce. Using the state-of-the-art 4D technology, we can capture over 100 body dimensions within a few seconds. We also have high-precision foot scanners for developing better-fitted safety shoes, as well as scanning systems for hands, objects, and workspace layouts. We will also mirror the Stride's data collection at work sites and training centers across all of Ontario through our mobile labs. By taking research into the field, we will capture anthropometric and strength measurements from thousands of construction workers and first responders.
How we study, address, and prevent workplace injuries is going to completely change. Participating organizations will have the opportunity to improve their safety culture and job accessibility. This will help them comply with relevant legislation. It will demonstrate leadership in advancing the workforce by contributing to job-specific databases. These databases will ultimately support better fitting and functioning PPE, tools, and equipment. That means better fit and function for everyone in the workforce, regardless of gender and race, and fewer workplace injuries. We can improve well-being and optimize the productivity of the Canadian workforce, and we're proud of that. Join CISWP and let's work together to make Canadian workplaces safer and more prosperous. Better data,
Better data,
Better data, safer work.
safer work.
safer work.
Thank you guys very much. That was a very, very informative presentation. This may not be something you can answer, but are the manufacturers of the exoskeletons committed to making equitable exoskeletons for all body sizes? Or are they more focused on men's bodies for now as they explore the science?
Yeah. So when you guys hear me, yes. So we work with healthy exoskeletons, and they are always open to get some feedback from us. So they provided to us the exoskeletons, and we were able to bring them to the field to ask people how they were the perceptions of the exoskeletons and to try it in the lab as well. And they're always open to know how can they improve the design. So I feel like that's the goal for the future, to keep including these feedback into the improving of the designs of the exoskeletons. Yes.
Okay, perfect. Here's another one. They're just coming in, so I'm not going to be able to read them ahead of time. I noticed that all force applications for drilling were horizontally applied forces. Is there plans to repeat the study for vertical overhead applications, like applying forces vertically into a ceiling?
Yeah, that would be nice. That's a great question. We chose the drilling because that's kind of like the most common task among construction workers. But we know for sure that there is a lot of people that perform that vertical, like horizontal drilling, and we saw it in our field studies as well. So yes, it would be nice to create these. This was kind of like the first step to create these tables for maximum loads. And the first step, we did it for the unilateral overhead drilling, but in the future we can expand that to other tasks and other movements that are like common in the skill trade.
Okay, good, perfect. One more I have here. The person wrote, perhaps I misunderstood. Did the exoskeleton only reduce, okay, I'm trying to read it as it moves, sorry. Did the exoskeleton only reduce anterior deltoid activation by 3% during the above shoulder work tasks?
Yes, that's correct. That's what we saw in our study, right? It's not like a generalized assumption. So we know that in other literatures, there was a bigger reduction in muscle activation, but this was significant. And it's just in 5 minutes, right? So it's a significant reduction in like a very short period of time. Yes, for the anterior deltoid, for the middle deltoid as well, we didn't notice the same for the posterior deltoid. Yes.
Okay. Which governing body will be responsible for enforcing the exoskeletons on organizations, or would organizations have a choice on deciding whether to purchase or not to purchase them for workforces?
So if they have the option, or if we want to force that?
That's kind of what I'm getting out of the question.
Oh, I see. Yeah. Yep. Yeah, for sure. Like this is a solution, like a potential solution for overhead work to reduce that the risk of injuries and to reduce that risk. Then it comes like, oh, do I want to implement this or not, right? So I feel like that's on the associations to decide on this and to see other alternatives. This is just one alternative. It's not the only one. So, yeah.
Okay, perfect. Okay, Trevor, we'll turn it over to you now.
Okay, thank you very much, Cristina.